4.5. We're looking at the substitution rule. And so last time we talked about indefinite integrals and definite integrals and how to find those by taking the antiderivative. Well, all we know so far is kind of like the power rule, right? But when we looked at taking the derivative of things, we had the power rule, we had the quotient rule, we had the product rule, and then we had more complicated ones, the chain rule, right? So here, but when we do integrals, all we have so far is that power rule, right? So we're going to introduce a new rule today. It's the substitution rule. So this allows us to find more complicated ones. We're not just taking x raised to something, right? Or the square root of x. So there's more inside. So now, like this integral down here, the integral of 2x times the square root of 1 plus x squared, that's a more complicated function, right? I can't rewrite those as half powers because I got a product here, right? And I got something inside a root. I got a function inside a root. So that's where we introduce a new variable u. And we're going to let u equal some part of this. So you can think, well, the trouble is, what do I let u equal? Well, I can let u equal 2x. I could let u equal 1 plus x squared. Or I could let u equal the square root of 1 plus x squared. The key in trying to determine which one of these I should pick is taking the derivative of them. So the derivative of this one would be just 2. The derivative of this one would just be 2x. And the derivative of this one is chain rule, so it's a little bit more complicated. But it would be 1/2, and then leave the inside the same, drop the power, so that's -1/2, and then times by the inside, which is derivative of the inside, which is 2x. Okay, so those 2's would cancel, and you get something like this, x over the square root of 1 plus x squared. Okay, so those are the derivatives, all those three. Okay, so what you look for is, we kind of got to think back to differential equations a little bit, because normally when we take the derivative, it's dy over dx, and then differential, we talk about this as a ratio, and when we take the derivative, we can multiply both sides by dx, and we can solve for dy, right? dy equals basically our derivative times dx. Well, the same thing is true here. It's just we're going to do du over dx. So we're going to multiply both sides by dx. So this derivative is u prime is equal to 2 dx. U prime is equal to 2x dx. And this one would be that dx at the end. Okay? And then what we're trying to do is we can substitute our u in based on what we have here. Okay? And then we look at that derivative and say, is that derivative equal to, somehow can I rewrite it to equal what's left, right? So if I let this be my u, 2x, is my derivative right here equal to what's left after I substitute in my u? It's not, right? So I can't use that one, okay? If my u is 1 plus x squared, so if my u is what's in the inside here, it's right here, if that's my u, does my derivative equal what's left? 2x dx. It does. So that means this one is going to be what my u is going to equal. Okay? This one's a little too complicated, right? That's not going to equal what's left when I substitute that in. So if this whole thing was u, this whole thing right here is u, again, that derivative does not equal what's left, 2x and a dx. So this is my u. So again, it takes some practice to figure out what u is. Sometimes it takes some experimenting, but usually you're going to let u equal whatever's underneath the radical, so whatever's underneath the square root, cube root, that kind of thing, or whatever's being raised to a power. So here's some examples. So if I have this example, here's my function that I'm taking the integral of. I'm going to let u equal 1 plus x squared. If I have an example like this, taking the integral of that, I'm going to let u equal x squared plus 1. And then the differential of du, I just talked about this. Basically, you take the derivative and add dx to it, right? And then you want to solve for, basically, you want to solve for what you're missing. So you let u equal some function, you take the derivative of that, multiply by dx, and then you start substituting in. So we'll go ahead and do a few examples of how this kind of looks. I mean, I can finish this one for you. So if we let that, let's go ahead and just do that one. So this is 2x square root of 1 plus x squared dx. So there's the integral of that. And this is the indefinite integral, right? So I'm going to let u equal 1 plus x squared because the derivative of that is just 2x dx. And then I'm going to plug in my u. So the integral of 2x square root of u dx. And then I'm just going to rearrange this, right? So I want to put u to the 1/2 because that's square root. And then I want to put the 2x and dx together. Because when I take the derivative of u, it equals 2x dx. Okay, so a lot of times you'll see this not written as prime. I've been doing videos mostly written as prime, but go ahead and let that prime just equal du. It's like the differential. Okay, so now what I'm going to solve for is I'm going to solve for this because I want this out. I don't want two different variables, right? I have a u, so that means I need to have a du on the outside, not a dx. Okay, so I want to solve for what's left. These two need to be the same. So then I can substitute du for 2x dx. So the integral of u 1/2 du. Now I can go ahead and take the integral of this. Okay, because now I can just use power rule. Right? I add 1, which is 3/2. U divided by 3/2, which is 2/3. And then I'm adding c to that. All right. But first now I can plug back my u. My u was 1 plus x squared. Add c. So there's my derivative. Or there's my integral. Sorry. There's my integral. I think, yep. So here's some kind of technical language for you. Whenever we want to write the integral of our function, if we can rewrite that in terms of the function evaluated at a function inside a function and the derivative of that inside function, then we can substitute in our u. All right, so basically the kind of same thing I was. Basically, you need to find out what u is, let u equal something, that the derivative of u equals what's left, right? What's left in here. So then you can substitute and you only have u as your only variable in there would be a u. So basically you have to substitute in something for u, take the derivative of that, substitute that derivative in so that you only have one variable, u. All right. Then we just add c at the end if we're finding the indefinite integral. If we're doing a to b, then we'd have to plug in a and b in, and b f of b minus f of a, right, for the definite integral. Okay. So that's kind of how the substitution rule works. So you might see it like this in this form. Looks like this. You just got to be careful kind of at the end when you take the integral of u. At the end you have a u from a to b or whatever it might be. Then you substitute in back in your what u equals. So then you'll have some x in there, and then you can take your a to b. That's what this is saying. Because I have a u in here, that means this would be actually not quite b. This is plugging in b into the x into the u equation. So that's why I probably should substitute back in what x is and then plug in your a and b when you're doing the definite integral. All right. So that's pretty much it. So that's it, but here's a couple examples. So here I'll let u equal 2x plus 1. So I like to substitute right in the start. There's u. Still have a dx out here. Okay, then I take the derivative of that. So du equals 2 du. And so now I'm trying to manipulate this thing. Oh, there's dx. Manipulate this thing to look like what I don't have. Okay, what I don't have a u in. Because now here's my integral. I need this integral because I substitute u. I need this to only have u's in it, but I have this dx here. So I need to take this derivative and solve it for dx. So dx equals du over 2. Okay, so now I can substitute this dx for du over 2. Du over 2. Now I can apply my integral rules that say I can bring that 1/2 out in front. I can rewrite the square root as a half power, and now I can go ahead and take the integral. So 1/2 u 3/2 divided by 3/2, which 2 is going to cancel, so I get 3u 3/2 plus c, since it's an indefinite integral. And then I can go ahead and plug in my x back in, so 3, this was 2x plus 1, 3/2 plus c, so there's actually my answer. Make sure you substitute your x back in, or what u equals back in. Okay, so here's another quick example. We know what the integral or the antiderivative of cosine is, but we don't know what it is of 5x. Okay, so here we're going to have to let u equal 5x. Take the derivative of that. That just equals 5 dx. Okay, so then substitute your u in. So we know the integral of cosine, because it's just cosine of x, cosine of u, but we still have this dx out here. So I need to solve this equation for dx. So again, we just divide by 5. Now I can substitute that in, cosine of u, and it's du over 5. So I can rewrite that using my integral rules. Put that 1/5 on the outside. This is cosine of u du. Now I can take the integral of cosine, which is negative sine. And so once I can do that, then I can, or sorry, it's just plain sine. So this is just sine of u times 1/5. Then we can substitute our u back in, which is 5x. And then add c at the end. So there's our integral. Okay, and then maybe here's another one for you. And we'll just come back to this one, but we'll go ahead and say from 0 to 4. So you do it the same way we did this one, but it's from 0 to 4. So that means right here you could see would be 1/2, or I guess 3 u to the 3/2, and that would be from 0 to 4. So I don't want to put 4 in for u, because this 4 and this 0 actually go in for my x. So that's when you need to substitute it in. And then we can go ahead, that was 1, here from 0 to 4. Now I can go ahead and plug in my 4, and then subtract, plugging in my 0. Okay, and then you can simplify this, so that's 8, so that's 9. Square root of 9. Square root of 9 is 3. 3 cubed is 27. 27 times 3 is going to be 81. So you get 81 here. Here you get 0 plus 1 is 1. 1 to the 3/2 is just 1. 1 times 3 is negative 3. So then you get 78. And so there's the answer for that. Okay, so that's kind of how you're supposed to do this substitution rule. You let u equal some form of the function, usually what's underneath the square root or what's being raised to a power, and then you can then you take the derivative of that, and then you substitute in your u, and then try to solve for whatever's left that has an x in it, because all you want when you take the integral is something with a u and du. Okay, and so that's it for this section.